Good morning. Welcome to Algebra class. From this week, our lesson is about properties of exponential functions from 7-2, textbook pages 442 to 450. Before we start, I want you to prepare the following: your algebra textbook, your pen, and your copybook.
What is a natural base exponential function? Well, the name of this function may be a mouthful, but the function itself isn't so bad. A natural base exponential function is actually a special kind of exponential function. So let's start off by recalling that. An exponential function is a function that follows this form: f of x equals a times b to the x. Here we have a variable in the exponent, so we have an exponential function. And if we want to see an example of that, we could have f of x equals 2 times 5 to the x. Neat. Now, a natural base exponential function has a special base. That base is the natural base. The natural base, remember, is e, an irrational number. So we would have f of x equals e to the x power. Notice, we have e as the base, and we still have a variable in the exponent, so we have an exponential function. But because e is the base, it's called a natural base exponential function. Remember, e is an irrational number that we can approximate to be 2.71828. So, now that we've seen what a natural base exponential function is, let's go ahead and take a look at the graph of this type of function. So, we'll draw out a coordinate plane with our x and y axes. Then, let's label a couple of special points that we can find for this function. This point right here, and this point right here. Here we have the point 0, 1. Our x-coordinate is 0 and our y-coordinate is 1. So if we take that x-coordinate and plug it into our function, we would have e to the 0 power. And e to the 0 power is 1. So that gives us the point 0, 1. Our other special point is this point, the point 1, e. Here, if we take that x value of 1 and plug it into our function, we have e to the first power. E to the first power is just e. So we get the ordered pair 1, e. And here we have it plotted right there. Remember, e can be approximated as this number. So now, let's take a look at this graph. This is the graph of the function f of x equals e to the x. As you can see, it sort of starts out flat, and then raises up quickly as your x's increase. Now, this function also has a horizontal asymptote. That asymptote is along the x-axis, the line y equals 0. If we look, this graph will go on and on forever, but it will never cross the x-axis. It will never cross the line y equals 0. In other words, there is no x value that we can plug into this function that will ever give us a y value of 0. So now that we have the graph of this function, let's go ahead and use it to identify the domain and the range of this function. Let's first find the domain. The domain, remember, is the set of x values that our function can have. Well, if we use our graph, we can see that our graph goes off in this direction forever and ever. Here, our x values can keep decreasing forever and ever. And if we look the other way, our graph continues on and on, so our x values will continue to increase. So that means that our domain is all real numbers. Now that we have the domain, let's find the range. The range, remember, is the set of y values that our function can have. And remember, we have a horizontal asymptote at y equals 0. We know that y cannot ever equal 0 in our function. We just can't make it true. And if we take a closer look at our graph, we see that there are no points below the x-axis. when y is negative. If we take a look at our function, we will never be able to have a negative y value. So y cannot be 0 and y cannot be negative. If we take a look, y needs to always be positive. Our range is all positive real numbers. So remember, the natural base exponential function may be a mouthful, but the function itself isn't so bad. Here we have f of...
In this problem, you will graph a function of the form y equals a times b to the x power. How does the graph of the function y equals negative 1/3 times 3 to the x power compare to the graph of the parent function?
What we need to think, which x values should we use to make a table? So we will use x equals to 0 and then choose both positive and negative values. So for x, we have negative 2, negative 1, 0, 1, and 2. And then substitute the value of x from y equals 3 to the x power. From negative 2, we'll have 1 over 9. Negative 1, that is 1 over 3. For x equals 0, we have y equals 1. And for x equals 1, we have y equals 3. And for x equals 2, we have y equals 9. For the values of y equals negative 1 over 3 times 3 to the x power, we have for x equals negative 2, y equals negative 1 over 27. For x equals negative 1, y will be negative 1 over 9. For x equals 0, we have y equals negative 1 over 3. For x equals 1, we have y equals negative 1. And for x equals 2, we have y equals negative 3. Each value is negative 1 over 3 times corresponding the value of the parent function. After that, we need to graph the functions, plot the points. So the negative 1 over 3 in y is equal to negative 1 over 3 times 3 to the x power reflects the graph of the parent function, y equals 3 to the x power, across the x-axis and compresses it by the factor of 1 over 3. So the domain and asymptote remain unchanged. The y-intercept becomes negative 1 over 3 and the range becomes y is less than 0. Get it number 1. Question. How does the graph of y equals negative 0.5 times 5 to the x power compare to the graph of the parent function? Our parent function is y equals 5 to the x power. Again, for the values of x, we will use negative 2, negative 1, 0, 1, and 2. For the parent function, we will substitute or plug in the values of x. For x equals negative 2, we will have y equals 0.04 or 4 hundredths. For equals negative 1, we have y equals 2 tenths. For x equals 0, we have y equals 1. For x equals 1, y equals 5. And for x equals 2, we have y equals 25. For y equals negative 0.5 times 5 to the x power, if x equals negative 2, y equals negative 0.02 or negative 2 hundredths. For equals negative 1, y equals negative 1 tenths. For x equals 0, we have y equals negative 5 tenths. And for x equals 1, we have y equals negative 2 and 5 tenths. And last, we have x equals 2, y equals negative 12 and 5 tenths.
In this problem, you will translate graphs of functions of the form y equals a times b to the x power. How does the graph of the function compare to the graph of the parent function? Part A. The first function is y equals 2 to the power of x minus 4. How is the graph of y equals 2 to the power of x minus 4 different from the graph of y equals 2 to the x power? The graph of y equals 2 to the power of x minus 4 is a horizontal translation of the graph of y equals 2 to the x power to the right 4 units. Step 1. Make a table of values of the parent function y equals 2 to the x power. Use both negative and positive numbers for the x values. Choose integers that will make calculations easy. Substitute each x value into the equation y equals 2 to the x power. When x equals negative 2, y equals 1/4. When x equals negative 1, y equals 1/2. Continue to substitute each value of x into the parent function to find the y values. Step 2. Graph y equals 2 to the x power and then translate the graph 4 units to the right. Start by plotting each point from the table. You've now graphed the parent function y equals 2 to the x power. Now translate the graph 4 units to the right. You've now graphed the function y equals 2 to the power the quantity x minus 4. The x minus 4 and y equals 2 to the power the quantity x minus 4 translates the graph of y equals 2 to the x power to the right 4 units. The asymptote remains y equals 0. The y-intercept becomes 1/16. Part B. How does the graph of the function y equals 20 times 1/2 to the x power plus 10 compare to the parent function? Where have you seen this situation before? The graph of a function like y equals 20 times 1/2 to the x power plus 10 is both a stretch and a vertical translation of its parent function. Step 1. Make a table of values for y equals 20 times 1/2 to the x power. Substitute each x value into the equation y equals 20 times 1/2 to the x power. When x equals negative 1, y equals 40. Continue to substitute each value of x into the parent function to find the y values. Step 2. Graph y equals 20 times 1/2 to the x power, then translate the graph 10 units up. You've now graphed the function y equals 20 times 1/2 to the x power. Now, translate the graph 10 units up. Translate each point up 10 units. The plus 10 in y equals 20 times 1/2 to the x power plus 10 translates the graph of y equals 20 times 1/2 to the x power vertically by 10 units. It also translates the asymptote, the y-intercept, and the range 10 units up. The asymptote becomes y equals 10, the y-intercept becomes 30, and the range becomes all real numbers greater than 10. The domain is unchanged. Use a graphing calculator to graph y equals 20 times 1/2 to the x power plus 10. The graph of y equals 20 times 1/2 to the x power plus 10 checks.
Static number 2 question. How does the graph of the function y equals 4 to the x plus 2 power compare to the graph of the parent function? Step 1. Make a table of values for the parent function y equals 4 to the x power. 4 equals -2, y equals 1 over 16. For x equals -1, we have y equals 1 over 14. For x equals 0, we have y equals 1. For x equals 1, we have y equals 4. And for x is equal to 2, we have y equals 16. Step 2. Graph y equals 4x, or 4 to the x power. Then translate 2 units to the left. The x plus 2 and y equals 4 to the power of x plus 2 translates the graph of y equals 4x to the left 2 units. The asymptote remains y equals 0. The y in